Okay, so continuing the theme of analog studies. So I'm talking about a different vehicle, which you can see is not designed to be skinny and not to fit down a hole, because it's exactly this point that Bill was just making, that different people have been pursuing different things in different ways. For those of you who know me that think about when it comes to where I intersect with ocean worlds communities is a long-standing obsession with going off to find out what's actually living at different vent sites at different seafloors in different ocean basins. And the thing that I need for my complete set on this planet is the Arctic. So that's really what I've been thinking about and designing a vehicle that will actually be able to go and do that stuff. And just like Bill was just saying, it takes 3 field seasons to do anything that you really want to do. And so our 3rd field season is just coming up this fall. And so that's what I'll be talking about a year hence, or in some future research will be what it would actually happen when we did actually go find some vents on the seafloor in the Arctic underneath ice cover. But for today's meeting, as we started discussing earlier today, there's lots of good reasons why when it comes to other ocean worlds that it may not be the seafloor is actually like the really cool place. That may well be where there's a big flux of reductants into an ocean, but if the ocean's already reducing anyway, then it may be up at the top here, might be where there's a really important redox gradient. So it may well be that this is actually the place, this is as far as we need to go. We don't need to make life so hard that we need to go down to the seafloor. There might be some oceans where it's actually perfectly adequate just to get here and go look for, I think Alison had a really nice cartoon earlier today from Mike Russell's paper about biofilms that could be forming along this surface instead. So it's a bit like we were hearing yesterday that you can't actually freeze an ocean without going through its resonant frequency. It's also true you can't go to the bottom of an ocean without going through the top of it first. So happily, the vehicle that we've built, the Nereid Under Ice, actually has this mode of operation. So it turned out that the first phase, when we were really mostly doing engineering, and because we were pretty scared of what we were doing, then we didn't actually go deeper than 30 meters, but it does mean that we actually got to do a bunch of stuff that is actually quite relevant, it turns out, as I think about it, or I've managed to retrofit what we did to prove to you that it's relevant to the theme of this week's meeting. And one of the reasons we were scared is we were talking about tethers before lunch as well. Our tether is 1.5 times the thickness of a human hair. It's a single unarmed node fiber optic or optical fiber. So again, we have a battery-powered vehicle like this ice fin we were talking about this morning. In our case, it has to be able to operate as an AUV to come home. We routinely design it so that the cable always breaks. We don't come home till the cable is, well, we've once come home before the cable broke. But the only reason we trusted ourselves to go and do this stuff was that we actually knew how to run operate AUVs quite thoroughly in the first place. So this is a vehicle that all the while that the fiber remains intact, we can continue to have real-time human-in-the-loop communications, and then when the fiber breaks, then it can turn into an autonomous underwater vehicle. We can use acoustics and other tricks to actually bring it home, but it can basically take care of itself and keep itself out of harm's way. And by using this, so I mean, there are 2 nice things. What it allows us to do on this planet is we can actually have something about the size of a roll of duct tape can give you 20 kilometers of tether, so you have a lot of reach. You can go a long way laterally, so you don't have to be, if you're operating from a ship, rather than drilling a hole in the ice, which is kind of how I do most of my stuff, then it means you can actually go long distances. It also means that it actually makes for a very low payload. So if you actually want to launch it into Earth orbit, this is the tether that's about as light as you can get. You can't get anything much weaker or much lighter than a single optical fiber. So again, in field programs, in this case, this is a picture of my ship. So if you squint really hard, that's it there, the biggest research ship I've ever been on. For context, up in the Arctic. And this is how we tricked out our vehicle, the NUI vehicle. So it's basically coming out of a wood tool stable. It inevitably ends up looking like a scaled down version of an ROV, which in turn looks like a scaled down version of an Alvin submersible. So here's some normal sized humans for scale, just to prove that you couldn't put anybody inside this. It is a robot. And some of the distinctive things we've done here is because it's basically a lot of what we've approached is thinking about it as an upside down ROV that can actually land on basically if you all stood on your head, then everything else I tell you about now will be like looking at the seafloor. Up to including the fact that we actually have a thing that's designed, so it is going to be it is just being upgraded now, so it'll go to 5,000 meters. So basically, there isn't any depth of ice-covered ocean on this planet you couldn't go to with this vehicle if you wanted to, depending on whether you want to look up under sea ice or under ice shelves or under glaciers. In our case, this stuff has all been very shallow work in the Arctic, but we also have skids on the top, so you can actually land on the upper side as well. Admittedly, we tend to keep a lot more space between the two, because I get very claustrophobic. I wouldn't be able to do the stuff that the ice fin team were doing. It would freak me out. But one of the reasons for having the lateral capability as well is that some of the stuff I'm going to talk about is the kind of stuff that Alison was already talking about. We know that there can be biogeochemical cycles under ice. But most of the work that's been done up till now has been done with icebreakers. So it's not an unperturbed system. By the time you drive an icebreaker into the ice and wedge a hole, so this is basically the V shape that you leave behind and you reverse the ship back out. And there's already hints. If you look here, there's some of this browny green color. So people have known that there was life happening underneath the ice. There was some kind of photosynthesis happening. But you can hardly, by the time you get here and then lower your sampling equipment in, claim that this is an unperturbed system. So this is our vision of here's a 2-kilometer ice flow. You can just see a little dark line along the top. That's the far side. That's the next place where there's open water. And so the vision is that you could actually get up to the edge of some ice, in our case, drop a vehicle down, drive in underneath in an unperturbed way, then approach the ice-water interface from underneath, and actually have some idea, hope that you, like the ice doesn't know you're coming, basically. So this is the first little bit of video clip. I mean, one of the first things that was completely new to me is our vehicle is tricked out with lights ready for the aphotic zone, but of course in the Arctic, the ice is sufficiently thin that you actually do get light coming through. So in past years, I thought, well, then that's completely irrelevant to you guys and an ocean worlds community. We don't want to think about that, except that where it becomes interesting here is when we think about where the energy might be and why there might be life at an ice-ocean interface, it's because there was some missing factor X that's limiting, the reason you'd have biofilms at the top of an ocean world, at the ice-ocean interface, rather than at the seafloor, is because there's some missing ingredient. So for Europa, think oxygen coming down from the surface, and in this case, it's photon. Okay, so if you just suspend your disbelief a little bit, then we can keep going, and you don't have to walk out now. So photons become the interesting thing. The other thing I wanted to point out is that the ice shelf above this, when you actually went in from the surface, we had a completely flat terrain. So all the predictions were that there would be flat terrain on the underside and just ice peels from the ridges. Turned out there's a lot more complexity to the topography at the bottom as well. There's a lot of physical patchiness. And so the question becomes, okay, if you've got that physical patchiness, how does that work? So in terms of light transmission, we did a couple of things. The first thing is we could actually just do vertical profiles by actually just working in a single spot underneath the ice and looking up and down. We could see how the different wavelengths attenuate and actually see how the distribution of missing ingredient X varies in depth. But we're also able to show how there was spatial variability. In our case, it was because this is an aerial photograph looking down. This is actually looking at ice ponding. So you have melt pond sitting on top of the ice. That actually has a lensing effect. So it actually changes the ability for light to be transmitted through the ice that varies. So there's a patchiness here. So this is a survey now of a vehicle flying at a constant 30-meter depth beneath the ice and looking at the intensity of a particular wavelength. So it's both spatial variability. So in our case, it's because melt ponds are producing our missing ingredient X. There's varying fluxes of that. But if you had some kind of geologic process that's delivering your oxygen down to the surface of Europa, again, you should be ready for that kind of patchiness. And in our case, that patchiness then results in patchiness in where life is distributed. So that's what I'm showing here in these little pockets, little areas. In this case, it's photosynthetic algae. So it's this green stuff, and again, it's not all over the place. It's not a continuous biofilm. It's little pockets that are responding to the changes in the physics of what's happening there. And so we were able to look in that some more detail, that we were actually able to put down physical, chemical, and biological sensors on this system. So again, we were trying to actually pursue some of these robotic ideas of how do you do this stuff without having to bring samples back? How do you actually do all the work in situ to find out what's going on? So here again is our vertical profile. You can see we can get up to about 2.5 meters. That's where we're butted up against. This is sea level. That's the base of the ice. So we can actually see the light transmits nice and smoothly down below this. But in temperature and salinity, there's a lot of structure. So there's a lot of warming right up at the surface, just right underneath in those little pockets where the heating's happening. That's actually fresher water. We have increasing salinity, but there's lots of structure in this just in the first few meters. We're down to 30 meters here. So in that top 5 or 10 meters, there's lots of actual separate layers and stratification of things that are happening. And what you can see then is that the biology is also responding to that. So in fact, where the maximum chlorophyll is, where the maximum biological response is, isn't necessarily right at the ice-water interface, but it's in the vicinity of this area. So the physics of what's happening across the ice-ocean interface and into the boundary layer in the ocean is also dictating what's happening in terms of chemicals, the total sorts, and different chemicals I'll come on to, and also then how much biology happens in this area. And just to respond to that, I mean, this bit isn't really relevant to ocean worlds, but I'm going to show it to you anyway because it's super cool. One of the things I really had trouble with was actually focusing on that ice-water interface, and it's because there was a whole bunch of life that nobody predicted. So again, this is really just a gee whiz moment of like these things look like alien life forms to you, then nothing does. But the key thing was the marine biologists who actually sponsored us to come along and try out our robot on their ship were actually people who didn't expect this to exist. They went there and they asked us to bring our robot because they knew there was photosynthesis happening through the ice and there were algae forming up against the ice shell. They also had their sediment records, which they knew what kinds of things sank to the seafloor, and so they knew what lived in the ocean. And here was transparent, gelatinous stuff that was actually forming a more complex food chain than they knew about, but had no hard parts and left no record in the sediment record. So the biologists went there, we went and looked in a new way, and they found new stuff they weren't ready for. So whatever our vehicle does, that's a timely thing of, doesn't matter what other planet you're going to, but even on our own planet, you need to expect the unexpected. So putting all that together, how am I doing for time? Yeah, I think. Cool. Then what I then got interested in doing was then saying, okay, well then we know there's this biology, we know it's not necessarily right at the ice-water interface, it's in the vicinity of that stuff. How would you go about coming up with a robotic mission that tries to capture all of that stuff and that three-dimensional complexity? And so that's what we did, was basically parked up against an ice floe with the ship, was basically then ran out for about 1 kilometer. And then what we started trying to do was a combination of lateral surveys. So you can see we're doing this square wave raster pattern, but also putting in fence posts. So again, tether management became a real issue. If we were doing this entirely autonomously, we wouldn't have to worry about it. But because we were trying to keep the tether alive as well, we didn't. It's like Ghostbusters, right? Don't cross the streams. And if you drive back over a thing that has a single optical fiber with your propeller, you'll cut straight through it. So one of the things was actually working out on the way out. We were using our ADCP to work out which way the current was blowing, and then that dictated whether we were going to do our raster pattern this way or that way, depending on which way we would be flaking out the tail behind us. And so then at each of these little red points is where we then did vertical profiles as well to actually look at the vertical structure and see how variable that was. So here's that same survey, slightly rotated now to help with the orientation of our data. So this is, again, one of these data plots, a bit like the stuff that the ice-cream team was showing us before lunch. So here we are running out deep. This is our salinity. So you can see it's relatively salty water at depth at about 30 meters down. And then when we do these vertical profiles and do work up just below the surface at 10 meters, then you can see it's much fresher water. So you can see this variability of the physics between where it's salty and where it's less salty. We can then show that with our chlorophyll concentration, we can say there's much less biological activity when we're doing our deep run out to start the survey at 30 meters. But there's lots of variability again here. And again, you can see if you look in fine detail on these vertical posts, that the chlorophyll, the biological maxima, are not right at the interface, but they're actually distributed in 3 dimensions. It allows you to map out the biology in 3D. And then the other part we did was, which I think becomes relevant to thinking about ocean worlds type stuff, is you don't necessarily have to look for the biology itself if you're looking for a biosignature. So the other way you can do it is we were actually here using an in situ nitrate sensor to actually measure the uptake of nutrients so that we can actually, then so we can actually see a drawdown. So here we have higher nitrate concentrations at depth. So it has like an inverse relationship that we have lower nitrates. You can see both the nitrate consumption. So that's basically where I wanted to get to with the talk, was basically to say, how do we map this across to ocean worlds? Part of it, of course, is we need to actually come up with the new vehicles, the stuff that everyone else has been talking about today, of things that actually fit through the holes that we put the right payload in. But there's also the knowing what the payload needs to be and knowing what you should be doing with that stuff, which can be a combination of both physical sensors, but thinking about what the right chemical sensors are going to be, what the right kind of life detection signals are going to be, whether those are actually, what are the essential nutrients for life, or if you're Mike Russell, what are the things pooping out, and what are the waste products that you might be looking for as well. So that's the other thing that's coming on in parallel. We had the Tunnelbot concept yesterday as one illustration of the kinds of things. This is from Kate's poster yesterday evening. And then this one is a new ICAR program I'm just going to be spinning up in the next 5 years. Is actually coming up with a new theoretical approach to what could be happening, trying our best to be planetarily agnostic of thinking on a planet-by-planet basis. What are the kinds of things that could be giving rise to life, and where might those signals be? Would they be down at the seafloor? Would they be up in the ice? And if they're at the ice-water interface, what would they smell like? What would they taste like? And how would you find them? Okay, thank you.